Welcome back, everybody. In this lecture, we're going to go through the documentation example for the various tree methods. So now that we have that intuitive understanding of how these algorithms work, what we're going to do is dive into the documentation examples. We'll work through decision tree, random forest, and gradient boosted trees, and you'll see that it's actually very easy to swap almost any machine learning algorithm out for another, the way PySpark and MLlib have been constructed. We will also expand a little more from the documentation example and show some useful evaluation features, as well as how you can use multi-class evaluators on a binary classification. So let's open up a new Jupyter Notebook and get started. Alright, I've started a new Jupyter Notebook, and as a quick note, all the data that you need is available under the Spark for Machine Learning under the Tree Methods folder. There's all the data and all the notebooks for this lecture, as well as all the other lectures in this section. I've started a Spark session. I've called it My Tree, so we're ready to get started. I'm also going to do a couple more imports. I'm going to import from PySpark.ml. I'm going to import pipeline. And then I will also import classification models from PySpark.ml. So I will say from PySpark.ml, classification, import, and then the ones we want. I want a random forest classifier. I also want the gradient boosted, GBT classifier, so they kind of shorten it there. And then I also want the decision tree classifier. And let me put this more on a couple lines here. That way we can see them all. So random forest classifier, GBT classifier, and decision tree classifier. Now as a quick note, all these various tree methods, depending on how you actually apply them, can be used for regression as well. So if you have a regression problem that you're interested in applying random forest on, you could say from PySpark.ml regression, and then import, and then you can click tab here and see what models are available for you. But you can see here you have a decision tree regressor, a general or gradient boosted tree regressor, and if you start writing R, you also have a random forest regressor. So you can use all these models for regression tasks as well. And remember, for classification, if you have an ensemble of trees, basically what they're doing is they're taking votes to see what class the actual row should belong to. For regression, what they end up doing is they average all the guesses for that continuous variable. So we're going to deal with classification for the tree methods just because it's a little easier to evaluate. Things like root mean squared error are sometimes a little hard to tell or understand intuitively. Things like accuracy or area under the curve are a little easier. So let's continue on with classification. And what we're going to do is read in the actual data. So I will say data is equal to Spark read, and this is the documentation data, so it's in that kind of esoteric libsvm format. And then I will say load, and it's the sample libsvm data.txt, and that's already available for you in the tree methods folder. So run that. We have our data, and let's just show off that data, what it looks like. And because it's documentation data, it's already conveniently shown as the label and features column. So we don't actually need to do much with this. So we'll keep scrolling down. What we're going to do is just split this into a training set and a test set. So we'll say something like train data and test data is equal to data.randomSplit, and then let's do a 70-30 split here. Okay, so now what we can do is create the various models. Let's start off with the most basic one, a decision tree classifier, and then set that equal to decision tree classifier. We want to specify the label column as label and the features column as features, but right now if you look, those are already the defaults, so we actually don't really need to specify these. The parameter that may be interesting to specify, if you look at Shift plus Tab, are things like the maximum depth of the tree, the maximum bins, and things like minimum information gain. I encourage you to play around with those values, and if you're confused on how they may affect your actual decision tree, what you should do is do the reading in Introduction to Statistical Learning to learn a little bit more about the mathematical background behind those parameters if you want to mess around beyond the defaults. I'm going to leave everything default right now, and besides the decision tree classifier, I'm also going to make a RFC or random forest classifier, and I will also make a gradient boosted tree classifier, so we'll just call it GBT. So GBT classifier. So I have these three classifier objects. They're all using the default parameters. Something like random forest, if you do Shift Tab here, not only do you have things like max depth and max bins, but you also have a really important one, which if you expand on this, is the number of trees to use. Now 20 by default may be pretty low, especially if you have a really large data set. So what we can do here is say something like num of trees equal to 100. And There's no right or wrong answer for how many trees you should use. At a certain point, if you start using too many trees, you're not going to gain any more accuracy for the additional trees and additional computation. So sometimes what people do is they run multiple instances of different tree amounts, test their accuracy, and kind of see where that cutoff point is where they're not gaining any more accuracy or whatever they're trying to actually evaluate on whatever metric for adding more trees in. So the more trees you add, the more computation time, and at a certain point you don't get anything back for using more trees. Okay, so we'll set trees to 100. It's also fine if you just use the default. It shouldn't really make a difference given that we're kind of working with meaningless data here because it's just that random lib svm file. Now that we have these various classifiers, what you can do is actually fit them. So we will see DTC model is equal to DTC, and I will fit this to my training data. And we'll do this for all three of them. So let's create those three models and then say RFC for this first one, or the second one I should say, and then GBT for the third one. So once you run that, this may take a little bit of time because you're just fitting three models in a row. Once those models have been fitted, we can use them and transform the test data to get predictions. So I can say DTC preds is equal to my DTC model dot transform and then grab my test data. And I'm going to do that for all three of them again. So let's copy and paste this, and we will say RFC preds is equal to the RFC model on that evaluation or prediction or transformation I should say, and then GBT and GBT here. So basically doing the exact same thing for all three models, and then we can kind of compare them at the end. So now if we take a look at just one of these, I'll say DTC preds and then show them. So I'm going to, let's just say show. I have the label, the original features, and then raw prediction, the probability, and then the prediction itself of the label. Now if you look at all of these, for example RFC, this also looks really similar, has that raw prediction column, but GBT will not have that raw prediction column. So if you run GBT, it only has prediction itself. It doesn't have that raw prediction value. So when you're using something like a multi-class classification evaluator or a binary class classification evaluator, sometimes it has raw prediction as its default input column. You'll have to change that to prediction for GBT. And we show that in the very next lecture. So keep that in mind. But now that we've done this, let's show you how you can use an evaluator on this. So what I'm going to do is say from PySpark.ml.evaluation import. Now even though this is a binary classification data set, if I only do a binary classification evaluator here, I'm only going to be able to do stuff like the precision recall curve and the area under the ROC curve. But luckily with the multi-class classification evaluator, this will still work even though it's a binary class. And with this multi-class classification evaluator, I can do direct metrics such as precision, recall, or accuracy. And you can check the documentation, as we've shown in the past, for those actual metric names. But let's create a multi-class classification evaluator that works for accuracy. So I will say ACC eval is equal to a multi-class classification evaluator, where if you do shift tab here, it expects a prediction column called prediction and a label column called label. Well, we just saw all these preds, these data frames, those all have it. And then the metric name, the default is F1, but what we can do is say metric name to be accuracy. And again, check the documentation for all the various metric names available to you. But once you have that, what we can do is just evaluate. So I can say ACC eval, and I'm going to evaluate the predictions. So the predictions I have right now, let's just do decision tree preds, and I'm going to print something so this is labeled. So DTC, we'll say accuracy. So if I run this, we should see the actual accuracy. So accuracy is 100% for a decision tree classifier. That should definitely raise some eyebrows, but you should also note that this data over here is really easily fit. So it's highly separable, meaning even if a single decision tree has 100% accuracy, it's not a good sign as far as how hard the data was to separate. So keep that in mind. In the next lecture, we're going to do a much more realistic data set, and these numbers will be more meaningful, but the methods themselves won't change. So let's check out random forest classifier accuracy, RFC, preds. We also get 100% on accuracy for a random forest classifier. And finally, let's check gradient boosted tree. Now remember, gradient boosted tree, we were just using the default parameters, so we also get 100% accuracy. Not very helpful, I know, but the actual methods are the same. So again, in the next lecture on our own custom code example, we're going to see something much more realistic, and these numbers won't be so perfect. Okay, one final note that I want to show you is the ability to grab feature importance. So let's grab our model that's fitted. For example, our random forest model. I'm going to copy this, paste this here, and if you hit dot, tab, you'll notice that one of the things we can grab off of this is feature importances. So this is not a very good example to show this, but if you hit Shift Enter on this, essentially what you get is the feature itself and then how important it was. So the higher the number, the more important it was. Now, this is kind of a weird example to show because the vector was sparse and it had a lot of features in it. So I'm going to leave this just for now kind of hanging in the air. The reason for that is this is a really big part of your consulting project in this section. So I kind of want to just leave it out there, and I want you to explore the documentation on how this feature importance actually works as an attribute off the model, because you're going to be using it for your consulting project. So consider this just a really heavy hint for the consulting project, and I'm going to leave it at that. This is something you can explore on your own. If after viewing the consulting project solutions you still have questions on this, feel free to post them to the Q&A forums. But again, this particular data set is kind of strange to call feature importances on. It wasn't very clear what was going on. For the next code along project and the consulting project, it will be a lot more clear to you. So I won't mention this again until we get to the consulting project, but keep it in mind, it's going to be really useful for that particular project. Okay, overall, I hope you understand now how you can actually call decision tree classifier, random forest classifier, and gradient boosted tree classifier. And again, if you wanted to, these could all be used as regression models. Main things to get out of this is basically you should have a full understanding of how to use almost any model with Spark. Essentially, you just import it. You could use the defaults or set up your own parameters. Then you fit to the training data, transform any test data, or if you have test data or some data that doesn't have the labels already, you would just evaluate it. Then you get your predictions out, and then you can call your evaluation. Now you can only call these evaluation metrics if you have test data. If you have data where you only had, for example, the features, you didn't have the actual label, so you're kind of at the deployment stage, you're not going to be able to call the evaluator. Instead, you're just going to do the evaluation and show your predictions, as we've shown in the past before. And the second thing I want you to get out is that you can use this multi-class classification evaluator even on a binary metric or binary data set, and you can use metric names such as accuracy. This particular data set, not very fun because it's essentially perfect, but the next data set that we'll see in the next lecture, that'll become a lot more clear. All right, if you have any questions, feel free to post them to the Q&A forums, but hopefully by now, most of this is clear to you. I'll see you in the next lecture.